3. I Atlas have re-emerged. After weeks hidden behind our Sun, the third confirmed interstellar object ever detected has completed its closest solar approach, and what astronomers observed has rewritten their assumptions. According to preliminary data from NASA's STEREO, SOHO, and JWST satellite observatories, the object appeared distinctly bluer than our star during perihelion, an optical signature that contradicts basic comet physics. You're about to discover why this color measurement, combined with 9 other documented anomalies, has elevated scientific scrutiny to unprecedented levels. December 19, 2025, marks the moment when Earth-based instruments get their clearest view yet. Most comets brighten as they approach the Sun by reflecting starlight and outgassing volatiles. But what happens when an object's observed color suggests temperatures rivaling or exceeding the star it's orbiting? Understanding what makes 3I/ATLAS extraordinary requires examining each anomaly individually, then recognizing their combined improbability. On October 29, 2025, at 7:47 a.m. Eastern Time, 3I/ATLAS reached perihelion, its closest point to the Sun, at approximately 1.36 astronomical units, or 203 million kilometers. That's just inside Mars's orbit. At this distance, NASA calculates the object received roughly 770 watts per square meter of solar radiation. Natural comets, loose aggregations of ice and rock held together by weak gravitational forces, often fragment under this thermal assault. 3I/ATLAS showed no signs of breakup. But here's what complicated observation. The object passed directly behind the Sun from Earth's perspective. Ground-based telescopes saw nothing. The comet had been lost to view since October 21st during what astronomers call solar conjunction. Fortunately, 3 space-based observatories occupied positions where the Sun didn't obstruct their view. Stereo A, orbiting slightly ahead of Earth, monitored continuously with its coronagraph instruments. SOHO, stationed at the gravitational L1 point between Earth and Sun, provided complementary data through its LASCO cameras. And JWST, the newest U.S. meteorological satellite launched in 2024, resolved fine details with coronagraph imaging from geostationary orbit. These platforms documented something unprecedented. During September and October, multiple observation teams detected brightness increases, far exceeding typical comet behavior. According to a preliminary analysis published on AR-HIV, the luminosity scaled inversely with solar distance to the power of -7.5, meaning brightness surged dramatically as the object neared the Sun. JWST's CCO, one coronagraph detected luminosity extending approximately 300,000 kilometers around the nucleus, nearly the distance from Earth to our Moon. Imagine a glowing envelope the size of the entire Earth-Moon system, yet researchers admit the mechanism driving such extensive energy release remains, in their words, obscure. Then came the measurement that has dominated scientific discussion for the past week. Multiple coronagraph systems, LASCO on SOHO and CCO1 on JWST, independently registered 3I/ATLAS, appearing bluer than the Sun itself. Loeb's public response was unambiguous. This is extremely surprising. Here's why. In astrophysics, color directly indicates temperature. Our Sun's photosphere emits light at approximately 5,800 degrees Kelvin, producing its characteristic yellow-white appearance. Cooler objects emit redder light. Hotter objects emit bluer light. Dust particles surrounding comets scatter solar radiation toward longer, redder wavelengths, the same physics that makes Earth's sunsets orange. Any surface passively heated by solar radiation at 1.36 astronomical units should, according to standard thermodynamic models, reach temperatures roughly 20 times cooler than the Sun, producing distinctly reddish coloration. Previous observations of 3I/ATLAS in July and August showed exactly that, reddish tones consistent with reflected sunlight and dust scattering. But at perihelion, the color shifted blue. The blue shift presents two possibilities. Either our understanding of thermal radiation and dust scattering is fundamentally flawed in ways that somehow escape notice across centuries of astronomy, or the object possesses an internal energy source generating photons at higher temperatures than ambient solar heating would produce. Some astrophysicists suggest extreme solar interactions or unusual gas chemistry might explain the blue appearance through mechanisms not yet fully modeled. Others point to ionized carbon monoxide emissions as a potential natural explanation, though this remains under investigation. What's undisputed is that standard comet models didn't predict this observation. Loeb poses the question directly. Does 3I/ATLAS employ an energy source hotter than our star? This blue coloration at perihelion now joins a documented list of properties that, individually unusual, become collectively extraordinary. Let's examine what shouldn't exist but does, relying on verified observational data and peer-reviewed analysis. According to calculations published in multiple preprints, 3I/ATLAS's trajectory aligns within approximately 5 degrees of the ecliptic plane, the flat disk where our solar system's planets orbit. Objects ejected randomly from distant star systems approach from any angle across the celestial sphere. The probability of such close alignment occurring by chance, roughly 0.2% or 1 in 500, like threading a needle from across a dark room. During July and August 2025, spectroscopic observations revealed material being expelled not away from the Sun, as radiation pressure dictates for all known comets, but toward it. Researchers confirmed this wasn't an optical illusion from geometric perspective effects. The physics of this anti-tail behavior remains unexplained by conventional sublimation models. Preliminary size estimates from Hubble Space Telescope data suggest 3I/ATLAS's nucleus measures between 440 meters and 5.6 kilometers in diameter. Combined with observed density indicators, this implies a mass potentially 1,000,000 times greater than 1I/Oumuamua and 1,000 times greater than 2I/Borisov. Yet 3I/Atlas is moving faster than both at comparable distances. This violates expected correlations. Gravitational slingshots from origin systems impart velocity inversely related to mass. Larger objects move slower. A fully loaded cargo ship doesn't outpace speedboats. Yet here, we have precisely that anomaly. The object's trajectory brought it within approximately 30 million kilometers of Mars on October 3rd, close enough that ESA's Mars Express and ExoMars Trace gas orbiter attempted observations. It will pass within 97 million kilometers of Venus in early November, within 267 million kilometers of Earth on December 19th, and within 54 million kilometers of Mars on December 25th kilometers of Jupiter in March 2026, while remaining unobservable from Earth during its most thermally active period at perihelion. Calculating the exact probability of such multi-planetary proximity combined with peak activity solar conjunction is complex, but preliminary estimates suggest odds well below 1%. Spectroscopic analysis of the gas plume surrounding 3I/ATLAS revealed an unusually high nickel to iron ratio. While nickel exists naturally in asteroids and comets, it typically appears mixed with substantial iron content. The proportions detected around 3I/ATLAS more closely resemble ratios produced in terrestrial industrial processing of nickel alloys than primordial solar system material. As Loeb notes, you really need to separate the nickel from the iron to get it to the proportion observed in the plume around 3I/ATLAS. The only place where such an exaggerated proportion of nickel relative to iron can be produced is through industrial production of nickel alloys. However, skeptics argue we have limited comparative data from pristine interstellar material, making definitive claims about natural versus artificial composition premature. James Webb Space Telescope observations in August detected an 8:1 carbon dioxide to water ice ratio, among the highest ever recorded. NASA characterizes typical comets as dirty snowballs, 80 to 90% water ice. 3. I Atlas contains approximately 4% water content, drier than Earth's Atacama Desert. Jacqueline McCleary, assistant professor of physics at Northeastern University, explains that carbon dioxide ice sublimates turns from solid to gas far more easily than water ice. For 3 I/ATLAS to have started glowing as far out from the sun as it did was abnormal, she said, noting this unusual volatile composition offers clues about formation conditions in other star systems. Light reflected from 3 I/ATLAS exhibits extreme negative polarization properties not cataloged in databases of natural solar system objects, including 2I/Borisov, the only other confirmed interstellar comet. The physical mechanism producing this optical fingerprint remains under investigation. Analysis of the object's origin trajectory traces back, within margins of uncertainty, to celestial coordinates near the WOW signal detection of 1977, the most credible candidate for extraterrestrial radio transmission ever documented. 48 years separate these events. While directional precision across such timescales is difficult to establish definitively, some researchers note the coincidence warrants mention, even if it ultimately proves meaningless. Data analysis from perihelion observations suggests 3 I/ATLAS may have experienced forces beyond pure gravitational motion, specifically 2 acceleration components, one radial, directed away from the Sun, and one transverse, perpendicular to its orbital path. For natural comets, this typically results from asymmetric outgassing creating jet-like thrust. However, Loeb calculates that explaining the observed acceleration through outgassing would require 3 IATLAS to lose approximately 15% of its total mass during perihelion passage. Upcoming observations will test whether mass loss of this magnitude occurred. Alternatively, some propose the acceleration might indicate an internal propulsion mechanism, though this remains highly speculative pending verification of the acceleration measurements themselves. Which brings us back to the blue coloration documented by multiple independent coronagraph systems near perihelion. As Loeb stated, if its surface were simply heated by solar radiation, it would glow redder, not bluer. The temperature gradient is inverted. Therefore, unless our thermodynamic models contain fundamental errors that somehow escape notice until now, an internal mechanism must be generating higher energy photons than the surrounding radiation field would produce. Whether that mechanism involves exotic natural processes, ionized gases, chemical reactions, or plasma physics we don't fully understand, or represents technology remains the central question. When researchers multiply the individual probabilities of each anomaly occurring independently, ecliptic alignment at 0.2%, mass velocity paradox below 0.1%, timing precision at fractions of a percent, composition and polarization anomalies currently unquantified but seemingly rare, directional correlation astronomically improbable, plus thermal and acceleration behaviors contradicting standard models. The combined likelihood collapses toward values comparable to winning multiple consecutive lotteries. It's essential to note that these are preliminary calculations based on assumptions that may require revision as more data becomes available. Probability estimates depend heavily on how we define anomalous and what background population we're comparing against. With only 3 confirmed interstellar objects detected, 1 I/Oumuamua, 2 I/Borisov, and now 3 I/Atlas, our statistical baseline remains limited. Yet the pattern is undeniable. 3 I/ATLAS exhibits multiple properties simultaneously that individually challenge conventional models and collectively defy easy explanation. Loeb has proposed a Loeb scale ranking system, 0 to 10, where 0 represents a definitively natural object and 10 represents confirmed technology. He currently places 3 I/ATLAS a bit above 4, leaning toward natural origin, but acknowledging the anomalies warrant aggressive investigation. 3I/ATLAS is most likely a comet of natural origin, Loeb emphasizes, but there are 9 to 10 anomalies that make it rank highly on the scale. We have to collect as much data as possible to figure out the nature of this anomalous object. 3I/ATLAS is now moving outward from the Sun. Twilight observations from ground-based telescopes resumed around November 11th, with the comet visible in the pre-dawn sky through telescopes, though too faint for naked-eye viewing. On December 19, 2025, it reached closest approach to Earth at 1.8 astronomical units, approximately 270 million kilometers away, completely safe, posing zero impact risk. This represents the optimal observation window. The Hubble Space Telescope, James Webb Space Telescope, and dozens of ground-based arrays will train instruments on the object simultaneously. Europa Clipper, en route to Jupiter, may pass through the comet's ion tail between October 30th and November 6th, potentially sampling interstellar material directly for the first time in history. ESA's JWST spacecraft will attempt observations in November using multiple cameras, spectrometers, and particle sensors, with data expected back in February 2026 after JWST emerges from behind the Sun. NASA's Juno spacecraft may get imaging opportunities when the comet passes Jupiter in March 2026. What are scientists looking for? If 3I/ATLAS maneuvers in ways inconsistent with purely gravitational motion, changing trajectory without corresponding outgassing, that would constitute extraordinary evidence. If it exhibits geometric structures inconsistent with natural fragmentation patterns visible at high resolution, that would demand explanation. If radio telescopes detect non-random signals, that would represent potential technological signatures. Alternatively, if natural processes explain every anomaly, if researchers identify new physics governing extreme volatile sublimation, discover previously unknown plasma behaviors near perihelion, or find errors in current thermal and composition models, then textbooks will require substantial revision, advancing our understanding of cometary science and interstellar object behavior dramatically. Either outcome would be revolutionary. We're not studying ancient artifacts or decoding distant radio signals. We're observing, in real time, an object whose properties push the boundaries of current comet models, exhibiting thermal, compositional, and dynamic behaviors that don't fit neat categories. Whether 3I/ATLAS represents the most unusual natural comet ever documented, or something that requires rethinking our assumptions about what travels between star systems, one fact remains undisputed. Based on standard thermodynamic principles, a passive object at 1.36 astronomical units from the Sun should not appear bluer than the star heating it, yet multiple independent coronagraph systems recorded precisely that. As McCleary at Northeastern notes, it's a window into what the pristine material is for other solar systems, which is precious, and, in turn, helps us refine our models of what solar system formation can look like. Is our solar system common or rare? Loeb offers a more provocative framing. In case 3I/ATLAS were technological, its senders would have mastered capabilities that go well beyond our technologies. Science is better than fiction, because nature might be more imaginative than the best scriptwriters. Right now, spacecraft instruments are repositioning. Observation windows are locked. Research teams across 6 continents are analyzing photon counts and spectral signatures. 50 days remain until the December flyby. 50 days to gather data that may answer, or at least better inform, questions about our cosmic solitude. History isn't archived footage. It's streaming live, wavelength by wavelength, through instruments pointed at an impossible visitor. Whether 3I/ATLAS is the strangest comet physics has ever produced, or an object requiring new categories of explanation, the answer lies in data yet to be collected. December 19th approaches. The instruments are ready, and whatever 3I/ATLAS truly is, we're about to get our best look yet.